Okay, wonderful. We think we have things ready to go. So as I said, very happy to introduce Miguel Rodrigues today, who's going to be talking about discontinuous waves as opposed to dispersive waves of hyperbolic systems, but a frontier in nonlinear wave stability. And I think this is an important aspect that is definitely worthy of exploration in our seminars to try to bridge the gap between dispersive hydrodynamics and conservation laws. So thanks, Miguel.
Thanks. Okay, so first thanks to the organizers, not so much for my talk, but for the whole semester. I think this is a very nice event. Very glad to be here. Yeah, okay, so the second thing I'd like to say is I tried to prepare a non-technical talk, or not too much technical. So I mean, to achieve this, I've more or less split my talk in two parts. So one of them is just some kind of general introduction to stability theory. Okay, just a few comments about nonlinear dynamics. Yeah, there's an issue with sound. Okay, and the second one is focused on the specific case of discontinuous waves of hyperbolic equations. And okay, so I've cut most of the proof, so it should not be too technical either, but we'll see. So let me start with some general comments about large time dynamics, and I'll go back to the finite dimensional case. So okay, so the reference situation is you have some ODEs in finite dimension, and you look at some equilibrium. Okay, so a stationary solution. And I like to discuss stability, and I mean stability in the usual sense that you have a reference solution, and you want to be able to prescribe any neighborhood of the trajectory, and ensure that there's a neighborhood of initial datum, so that if you start there, you remain in the prescribed neighborhood initial for all time. Okay, and I'm interested in this plus asymptotic stability, meaning that you have this, and also the fact that there's a neighborhood of initial datum that is attracted to the trajectory. Okay, so that's a standard Lyapunov theory. And okay, and maybe I can say that what I want to do is for most of PDEs, get a kind of Lyapunov result. So something that tells you that if the spectrum is fine, then this is also true at the nonlinear level, and you can describe nonlinear dynamics. And okay, so for ODEs, we all know, expect the standard result telling you that, okay, the first thing you should do is you linearize. So you get something that is linear in V. Here it's constant coefficient. So to analyze this, then you go to a spectrum, meaning that you take a Laplace transform or you look at eigenvalues because we're in finite dimension. And if your spectrum is on the left of the imaginary axis, then you get exponential decay at the linear and nonlinear level. Okay? And the proof, okay, one of the proof is quite elementary. You just take this assumption, you prove that you get exponential decay at the linear level, and then you use it in a Duhamel formula, in a variation of constant formula. Okay, that's the standard proof. And what I'd like to discuss is what can you do when some of these things fail. And I will start with what can fail already in finite dimension. And I'm only interested in the cases where things fail because of a structure. Okay, I only look at cases where what is happening is due to a robust mechanism, something due to the structure. And a typical thing that could happen that prevents you to getting this okay, exponential spectral stability is the fact that your equilibrium could be not isolated. Okay, it could be part of a family of equilibria, and because of this, when you take a derivative along your family of equilibria, then you get some element of a kernel of the linearized dynamics. Okay, and that prevents you from getting a decay for everyone. And okay, but still, if this is the only issue, if all the rest is of the spectrum is far away and you have some exponential spectral gap, you can prove stability of the family instead of proving the family of the stability of one equilibrium. Okay, so meaning that when you perturb, you will move around your family. Okay, let me give you one example in finite dimension of these kind of things, where instead of looking at equilibria, I'm looking at a periodic solution. Okay, so periodic in time. Now, my reference solution is not isolated because I can always take it and translate it in time. So this is still a periodic solution. And because of that, when I differentiate with respect to the shift in time, I get an element of some solution of a linearized dynamics that is not damped. Okay, that is actually coming back to its initial value after one period. Okay, so this is exactly the kind of situation I was mentioning. There is an element of a linearized dynamic that is not damped. But okay, if this is the only issue in the sense that all the rest is damped, and this is happening just with multiplicity 1 due to exactly this, then you can prove exponential stability of in a sense that is called orbital sense, meaning that you look at the perturbation, but you don't compare it directly to the initial solution. You use a shift. Okay, you have to shift just to synchronize to say where you are in your family of translated version of the original periodic wave. Okay. No, periodic solution of the ODEs. Okay, so up to that, everything is as in the previous case. This is a bit harder to prove, but still elementary. And this is something that happens already in finite dimension. Now, I want to go to phenomena that are not happening in finite dimension, and typically that are due to the fact that here you see the spectrum is made of eigenvalues, so it's discrete. So either you are on the imaginary axis, or you have a gap. Okay, there's nothing in between, so you cannot come and touch and without leaving any room for a gap or whatever. Okay, so in infinite dimension, this is happening, and you have to deal with that. Okay, so yeah.
I don't know. Could we possibly just have you speaking in person, because I really want to hear what you're saying, but it's really hard to understand what the two.
Thanks. Yeah. Okay. 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 So I want to discuss now what you can do when there is no gap. Okay. So this is not this can happen only in infinite dimension. Okay, like for a PDE, not for an ODE. And the first comment I'd like to make is that a gap is required for exponential decay. And the second comment I want to make is that I'm interested in the linear decay only if it's good enough for nonlinear analysis. Okay, if you just look at the proof by Duhamel formula and so on, you see that essentially the condition you need is that the decay should be integrable in time. But then there's an abstract theorem telling you that if you have a decay that is not too weak, okay, so this is the precise condition, but it includes the case where the decay would be integrable in time, then you have an, oh, okay, sorry. What's going on? Yeah, okay. So if you have a decay that is not too weak, then you have an exponential decay. Okay, so this is a very abstract theorem that tells you that, okay, it seems to say that there's no hope for anything, but the trick is that it only works if you measure decay and initial datum in the same space. Okay, so in the infinite dimension, everything is the same. Okay, there's only one topology and everything is the same. In infinite dimension, you have room for a change in this, where you measure the data in some space and you look for the solution in some other. Okay, another way to say this is that if you don't have a spectral gap and you want decay, you have to give something away. Okay, so there's no free decay. Okay, you have to trade the decay for something else. And let me show you a few examples of this. That there are a few different mechanisms for that. Okay, like the first one I want to discuss is the case where you essentially you trade localization for decay. Okay, so it's a well-known case is if you look at the heat equation on the whole space. Okay, so you have room for spreading, and the spreading here is more or less due to the fact that if you go in the Fourier, on the Fourier side, all the Fourier modes are exponentially damped except for the 0,1, but with a different kind of a different decay rate. Okay, so it causes some spreading in space, and you may indeed trade essentially trade off localization for decay with some rate. And use, okay, it's quite intuitive what is happening. You're spreading with a scale square. You see that the more space you have, the more room you have for spreading, the stronger the decay. So in particular, if you think that I should now try to use this in a nonlinear argument, the critical dimension is the case where this should be integral in time. So it's dimension 2. Okay. So if you have just some random equation where you have some nonlinearity and then the decay that is like this, the critical dimension for the argument should be 2, okay? Meaning that you can run easily the argument for dimension higher. There's no hope below, and maybe you can deal with dimension 2. Okay. And so this is when you have an equation without structure. But if this decay is happening, in the cases I'm interested in, it's because there is a structure forcing it. Okay. So if there's no gap, it's because there is something in the structure. So usually by the structure you gain 1 dimension. Okay. So typically in the cases I'm interested in, this could happen, for instance, because my equation is a conservation law, and this will increase the decay on the nonlinear terms by 1/2. So the critical dimension will now be 1. Okay, so it covers everything. Okay, so this is one possible mechanism so that you can. Okay, but something that looks a bit like this is also dispersion. Okay, now the spreading is the same. So this is a Schrödinger equation, so it's square root of t, but it's not due to the fact that everyone is damped with different decay rate. It's due to the fact that everyone travels with different velocity. Okay, so it's if you fix c, this is just traveling but with a velocity that depends on c. Okay, and because everyone is traveling with different velocity, you still have decay. Okay. And you may think that the game could be a bit the same, but there is one thing that is different here, and which is that you cannot expect all the bounds to be true. Okay, the fact that you have square root of t spreading predicts the kind of scaling you expect for decay, but some of the bounds fail. For instance, okay, let me give an example. If you look for just LP to LP with no decay, because you don't give up anything, this is true only for p equal 2. Okay, so all the other ones fail, and that prevents you to do the nonlinear analysis in an easy way. Okay, because you have to count a bit what are the ones that are true, what are the ones that are not true, and here you are paying very much the fact that okay, things are not as nice as the heat equation. So I don't want to discuss too much details about this, but okay, the expected decay is the same, but there are some technical difficulties in this case. Okay, so that's all I want to say about spreading. So another, okay, maybe I can give one comment, is that it's not so bad to lose localization, because in a nonlinear argument, you gain back the localization. Okay, so if something is localized, its square is more localized. So okay, so then when you put some localization, you improve it by squaring, and then you give it back to get decay. Okay, so this is fine. Everything is just looping around, and you can close a nonlinear argument. Okay, so there's another case that is not so nice. That is mixing. Okay, where the decay is not due to spreading; it's due to some kind of averaging, and then you lose regularity instead of losing localization. And at the nonlinear level, this is very bad. Okay, because if you square, you lose regularity actually, in a way. So it's okay. So you have to get a good structure to help you close the argument. So let me give you an example that is a bit different. So instead of looking for large time decay, I have included some parameter epsilon that is encoding that I'm looking at large time. Okay, so instead of sending t to infinity, I replace t by t over epsilon, and I send epsilon to infinity and I want to show decay with respect to epsilon. Okay, and this is just an exponential function, so it's in n infinity, this should be of size 1. But if I'm ready to lose a bit of regularity, like measuring with -1 derivative, then this is of size epsilon. And to see this, okay, this essentially means that this is the time derivative of something of size epsilon. Okay, this is what this norm means. Okay, but and something that is different here compared to okay, it's actually better compared to localization. To the case where you get decay by localization, is that you can play this game as much as you want. For localization, you have a natural upper bound on the decay you can expect. Here, this is not true. If you are ready to lose infinitely many derivatives, you can improve it infinitely many times the decay. Okay, and this is easy to see in this particular case. Like if you are ready to lose k derivative, you get epsilon k. And on the Fourier side, it's more or less related to the same thing. It's like you're spreading on the Fourier side. So yeah. And if you prefer Fourier, you can also get this bound just by looking at Fourier and see that you are exactly doing that. Okay, so you can test this against a dual test function and then give up derivatives. Okay, so you may complain that this is almost useless because I mean, okay, you don't care about negative regularity and okay, so it will be useful only if you are inserting this somewhere where you integrate it back. Okay, so that you go back to n infinity, for instance. Okay, so this is useful only at a place where it gets integrated. Okay, so let me give you a simple example where this happens. Let's look at a Newton system. Okay, like there's some electric field and then a magnetic field that is constant in 2D. Okay, and you see what is happening here because of there's a strong magnetic field. Okay, of size of strength 1/epsilon, and I've scaled time to be in large time. And the second equation makes the velocity measure that, okay, because of E, it will be of size epsilon in W-1 infinity. So by itself, it's not very useful, but you see that V is appearing in the other equation. So in the other equation, it will get integrated to get the dynamics of X. So you get that it's of size epsilon -1 infinity, and then you put it here and get a contribution of size epsilon to X. This is exactly what you want, okay? And you play this game quite explicitly here. You may use the second equation that tells you that V is oscillating to get a better first equation like this. Okay. And here you may guess what should be the dynamics. When epsilon goes to 0, you expect that the main effect of the oscillation is that you'll get some electric drift. Okay. And you can play this game in more complex dynamics, and this is actually a key part of what you have to understand if you want to confine plasma by fusion devices. Okay, so there is this kind of things, and then you may also wish to build numerical schemes that are okay, sufficiently good to capture this kind of oscillation at least in the average dynamics. Okay, so there's an average dynamics, an average PD behind this, some kind of hydrodynamic limit. Okay, I don't want to discuss this too much. Maybe I can give an example of mixing that is really related to large time. A bit more complicated, not too much, but a bit. Just I'm looking at a free transport equation in kinetic formulation. So F is depending on time, space, and V. Okay, so this is a distribution of position and velocity. If I were in space, if I were on the whole space, I would get dispersion and decay by dispersion. Okay, but here instead of that, I'm putting myself in a torus. Okay, so everything is confined. So things that are trying to travel at different velocity, they just wrap around. And so they average because of this. And if you want to measure this without negative regularity, you may just integrate in velocity, and you'll get that this actually becomes constant with some rates, and the rates depend on how much derivative you're ready to lose. Okay, and this is very easy to get. Okay, again, you can see it in on the Fourier side if you prefer. And this kind of mechanism of decay is the one that is appearing, for instance, in Landau damping or inviscid, sorry, or inviscid damping for Euler equations. And the point is that this is useful there because okay, first you integrate and then you solve the Poisson equation. So you do integrate many times to get back regularity. Okay, I don't want to discuss this too much. So this is the discussion about what you can do when there's no spectral gap. Okay, what kind of decay you can get in infinite dimension that you will not get in finite dimension. And another thing that I want to discuss is in infinite dimension, there are things that are worse than orbital stability. Okay, there are cases where the notion of stability you have to use is even worse than what I've shown you for the periodic solution in time. And the worst case is the case where you have to essentially synchronize both in time and space. Because you're probably used to the case where you have a solitary wave, and then you do a perturbation, and it moves in time, and so you have to shift in space at each time. Okay, and for periodic wave, this is worst. I mean, we have a notion of stability that is adapted, something that we call space-mounted stability, and that corresponds to that. So we have now a quite general treatment of this for parabolic equations. Okay, so if I take a periodic wave of parabolic equation on the full space, and if it is spectrally stable in the sense related to the diffusive kind of decay I've shown you before, then we can prove nonlinear stability in some space-mounted sense that I will explain right now. Okay, and it's related to orbital stability, but it's worse. Okay, Okay. So I'll try to explain a bit this picture, but you may have in mind that what is happening essentially that a periodic wave is an array of infinitely many bumps. And when you add a perturbation, then you'll create some shift everywhere infinitely many times. So you have to shift all the cells to synchronize before doing any comparison. Okay, this is more or less the spirit of what is happening. And let me show you this on a circular picture coming from a numerical simulation. So, okay, so this is space, this is time, and we are trying to follow the position of each of the bumps of the periodic wave by looking at the local maximas and local minimas. Okay, and we are in the reference frame of a wave. So if there were no perturbation, you will just see straight lines, okay, just because the wave is not moving, and so the local minima stay where they are, and local maxima also. So instead of that, we have added a perturbation more or less localized here. And what is happening is that the perturbation is dividing itself in a few pieces. Each piece is traveling with its own velocity, okay, what is called the group velocity. And as it moves, it interacts with all the bumps. So they interact for some time. And after the interaction, the main effect is that there's a shift. Okay, and after the interaction, it just goes straight again, but with a shift. So you see, for instance, this guy goes straight, interacts a bit, and then he goes straight again, but with a shift. And what is happening in the end is that you have cut your space-time diagram in a certain number of cones, and in each cone you see a different shift. Okay, so if you want to do a comparison and get something that is close, you have to essentially shift in a way that depends on where you are on space and time. Okay, at least in which cone you are. Okay. And okay, there are red lines there. Okay, I'm saying that they're coming from modulation theory, meaning that the group velocity, you can guess them from the Whittam system. They are just the characteristic velocity of the Whittam system. And if you want to get a large time description, you have to correct the Whittam system with diffusion terms, okay, in this system. But we know how to do that, so we have a diffusion version of the Whittam system that predicts also the large time dynamics completely. Okay. And okay, so if you want to measure a bit precisely what I said, that instead of comparing U to V, you allow for some kind of change of variable, but you want to change the change variable to be essentially just locally a phase shift. Okay, just so you add a weight where you weight the gradient of the difference between psi and the identity, so that locally it's almost constant. Okay, so this is what you control. So if you don't do that, what you'll see is that okay, in N infinity you just see a shift, so it's something of size 1. But if you integrate over a cone that is spreading with like t, in L1 you get t, in LP you get t to the power 1 over p, so it's growing. Okay. And so you may conclude instability just because you're not using the right notion of stability. Okay, if instead of doing that you use this kind of strange comparison metric, then you will remove the shifts and you will only see the perturbation. And the perturbation is decaying like with a heat kernel rate. Okay, so this is the rate of the heat kernel in one dimension. So it's you see really the bumps that are due to the modulation of dynamics. Okay. And okay, just to show one picture of dispersive equation. So this is the same thing, but for the linearized KdV equation. So it's linearized about a cnoidal wave. And I'm just showing the perturbation. So at a slow scale, you see essentially U prime. Okay, so these are straight lines due to U prime. And you see it's essentially a constant version of U prime in each cone. Okay, so essentially 0 outside, and then a 2 version inside the cones. So there are more cones than okay, initially, because the modulation system is of dimension 3. So there are 3 characteristic velocities. And in large scale, you also see the dispersive correction to the modulation system. Okay, like you have a airy kind of waves that are very much localized on one side and slowly oscillatory on the other side. Okay, you even see the sign of each of the dispersion correction to the characteristic fields of the modulation system. Okay, and this is proved also at the linearized level. Okay, so this is all for the like the general part of discussion of what are the things that are quite different if you go to infinite dimension, if you look at large time dynamics. And before moving to hyperbolic equation, I want to give a few examples. So okay, unfortunately the movies are not running. Okay, so this is steady, but you should see an array of periodic waves. Okay, and the same, I guess this is the same here. Yeah. If you go in a rainy city, this is quite easy to see. Okay, it's just you just look at the street, you see this kind of pattern very often. And okay, so these are called world waves. So this is an experiment. So this is much clearer to see, of course, much more neat. And of course, you may discuss a bit what should be right modeling. Okay, if you are ready to use viscous modeling, then the theory we already have is including these cases, and we have also looked very closely at the existence part, the spectral stability part. So, okay, I should have said this at some stage, but of course, the existence and the spectral stability part, it requires a case-by-case study. Okay, so for the Lyapunov theorem, you may expect to get something very general, but if for the existence and spectral, you need to use, I mean, you really need to study the problem you are interested in. Okay, so I'm trying to do both. Okay, but the most common way to model this is with hyperbolic equation. So typically with the Saint-Venant equations. And as solution of the Saint-Venant equation, it doesn't fit in any of the theory we have so far. And there are many reasons for that. Okay, I will try to explain a few of the problems. So one of them is, of course, that, okay, it's a periodic wave, so it's a bit harder to analyze anyway. But now we know how to do this with parabolic systems. So this is not the main thing. Another problem is that it's discontinuous. Okay, if you model this as an hyperbolic equation, this is an array of shocks. So there's an increasing part, and then it jumps, and then it goes on like this. And if you go back to just the initial proof of the Lyapunov theorem, the first thing you do is you linearize. Okay, and you use Taylor expansion, you use regularity, and so you lose almost instantaneously in the argument if you're not careful. So there is another problem that is also robust, that happening all the time in this kind of problem, is that there is a characteristic point in the profile. Okay, what does this mean? So okay, this is an hyperbolic system. So there is a first order part, but some of the coefficient in the first order part is vanishing. So actually, at some point, you are zeroth order instead of being first order. Okay, so there's a kind of loss of ellipticity, and it causes problem everywhere. Okay, everywhere in the theory, this has strong impact on. And there is the last thing that is a bit special to world waves in the Saint-Venant case is that there is an infinite dimensional kernel. Okay, so these are many difficulties. Okay, we are not able to solve all these problems, but what we have done is try to study simpler cases where you find one of these problems at a time. And I'll try to give you a few hints about what we know about a simpler case that is motivated by this kind of problem. I'll start with, okay, so for scalar equation, we have a complete classification. And it's not very technical, so okay, it's not so technical. Okay, okay. Let me recall that. So this is the kind of scalar equation I have in mind. So there's like a first order part and then source term, and it's in conservative form, so that I can give a meaning to being a solution even if I have discontinuity. So there is there's a good local Wapos-Ness theory due to Khrushchev. Okay, and you even have a notion of characteristic that is able to deal with this kind of solutions. So I don't want to insist too much. This is very old, classical, but everything is fine from this point of view. Okay, so I can move to nonlinear stability. And the first thing I'll do is I still need to be able to do Taylor expansion. So I will restrict to solutions that are piecewise smooth. Okay. So in this way, I can do the Taylor expansion in the smooth part and then look at the jump condition across the discontinuities and linearize this condition. It's more or less the spirit of this thing. And the first thing I will explain is the notion of solution you have to use in this case is not, okay, it can be a classical solution because there's discontinuity. It's not weak solution because that's not strong enough to get uniqueness. It's something adapted to the problem that is called entropic. Okay, and I will explain what this means on the piecewise smooth solutions. Okay, that's the one that I want to study. So in the smooth part, you're just solving classically the equation. And then along the discontinuities, you have some compatibility conditions. So the first one is that if you want to be a weak solution, a solution in differential sense, you have to satisfy Rankine-Hugoniot condition. Okay, so that gives you more or less in particular, that constrains the evolution of the discontinuity, but this is not the only thing in general. And this is not sufficient. Okay, if you stop here, you just have a weak solution, and that doesn't give uniqueness. You have to add something. And in this case, it's easy to state. The entropy condition is equivalent to Euler-Unique inequalities. Okay, so these are, if you have all of this, you are an entropy solution. Okay. And yeah, okay. I want to use piecewise smooth topology. So in particular, in my stability notion, there will be the constraint that when I do a perturbation, it will not create a new singularity. Okay, so the singularity that you see, they were originally in the unperturbed wave. Okay. And for this, of course, the hyperbolic equations, they are creating new singularities if you don't do anything. So you have to use the fact that the decay can prevent the formation of singularity. And okay, I'm explaining this on a toy equation that is very easy. This one you can completely solve explicitly under which condition you will form or not a singularity. And you see that, okay, if beta is 0, as soon as U0 is compactly supported, you form a singularity. But if beta is positive, then when U0 is small enough, okay, you don't create any new singularity, you don't form shock, you may remain with the notion of regularity you have initially. Okay, so that's why you have some hope that you could measure proximity by just using a piecewise smooth topology. Okay, because you will get exactly the same discontinuity structure as initially if the decay is strong enough. Okay, so let me give an example now of a stable wave. So the most simple, okay, the simplest one that is discontinuous is just a Riemann shock. Okay, something that is constant, constant. And if you want this to be a solution, the constant have to be 0 of the source term. The speed is prescribed by Rankine-Gogno condition, and then you also need to satisfy all unique inequalities, and I'm asking for them to be satisfied in a strict sense so that I can perturb them. Okay. Just then they are stable when I add a small perturbation to that. Okay. And then you can look at the spectral stability problem, and if you want an exponential spectral gap, these are the conditions. Okay, so you need to do a small computation to check that, but in the end, these are the conditions. And you can indeed prove stability, meaning that if you prescribe some perturbation of the shape, okay, so you perturb the shape initially, there may be a position, but it doesn't matter so much. Then there's a solution for which what you prove is orbital stability. Okay, you have to shift in time for the same reason as before. My wave is not isolated. You can translate it in space. So you have to adjust the position in shape, in position. You have to adjust the position, and here it's uniquely determined. Okay, because it is determined by where you have the discontinuity. If you want to compare in a strong topology, you have to first adjust the discontinuity exactly. And okay, there's an exponential decay rate that is sharp, and you control also the phase. Okay, you can actually prove that it converges to some constant in the end. Okay, so in the end you converge to some shift of the wave. It's okay. You cannot compute this shift in terms of initial data. It depends on a very nonlinear way from the initial perturbation. Okay, and in this case the proof is not too hard. Okay, so but it's very special to the scalar case. What you can do is first you prove stability of the constant state. Okay, so if you have a constant state, you can prove that. Then what you can do is that you have two smooth parts. You extend each of them to the full line. Use your first step, and then you solve the Rankine-Gogno to glue them correctly. And you can estimate all the things, and it works. Okay, but it's of course very special to the scalar case. Okay, and in particular, if you look at the spectral problem associated to this notion of solution. Okay, so you get interior equation, and you get a transmission equation. So what, like a linearized version of a Rankine-Gogno and spectral version of that. What is special to the scalar case is this equation is scalar also. Okay, and so you can think about this as being of the same type as before, but for psi. Okay. If instead of that you have a system, then this is a system equation, but still psi is a scalar. So it's quite different. You cannot solve it only with psi. What is special here is that you can solve things only with psi once you know the solution of the two of our equations. Okay, so for the system case, it's not like this. So there's no trick for the system case. And you may also check that indeed lambda equals 0 is a simple eigenvalue. And if you want the eigenvector, you just have to take u equals 0 and psi 1, and it works. Okay. So I've already said that we have a full classification. So I'll go to classifications. Okay, so this is one example of a stable one, but there are actually a huge number of traveling waves for this problem, because you can essentially take a traveling wave part, jump, take another traveling wave part, jump. In particular, you can jump infinitely many times, and you can have infinitely many jumps without being a periodic or whatever. Okay, you can have the structure you want for a jump in general, because you have a very huge number of traveling waves. But what we will see is that there's only a few of them that are nonlinear stable. So there is when you use the stability criteria, there's a huge reduction. I want to explain that now. Okay, so first I will just introduce the notion of a wave I want to consider. I'm excluding the non-degenerate one. Okay, so I will explain what this means. So I have to solve this in an entropy sense, and moreover, I'm excluding the case that if you have a characteristic point, then it's not degenerate. Okay, and if you have some limit at infinity, then these limits are not characteristic points, not characteristic values. And I'm also excluding that the case that they are, if you are 0 of G, they are not a 0 of G prime. Okay, so these are the kind of non-degenerate condition I want to include. And I already say that I'm asking for strict Orlenic condition, as in the Riemann shock case. Okay, so this is what I mean by non-degenerate. And these are some direct consequences, like the fact that because my equation is first order, this implies that the smooth parts are all monotone. Okay, maybe constant, but yeah. That's it. And if I have two shocks, then I necessarily have a characteristic point. Okay, because of the Orlenic condition, they imply a sign of f prime minus sigma, and the sign is different depending on whether you're on the left or the right. So it has to vanish somewhere in the middle if you are between two shocks. Okay, so the fact that there will be a characteristic value in the profile is something robust. It's happening as soon as you have two shocks. Okay, you're done. You have a characteristic point. So this includes, of course, the periodic case where you have infinite many shocks. Okay. So what are the possible instability mechanisms? Okay, so we already more or less seen the one coming from infinity. Okay, so if you have a wrong sign for G prime, then you'll get instability at infinity coming from just a constant coefficient case at infinity. Okay, and maybe I should insist on the fact that we have proved that this implies this at the spectral level, but also at the nonlinear level. Okay, we have a full classification at the nonlinear level, meaning that we have proved that this is also nonlinearly unstable. So another kind of mechanism is that at a characteristic value, if it is dissipative, then you have instability. Okay, that's a bit counterintuitive. But it's coming from the fact that if you are dissipative at a characteristic value, then the characteristics are going to the characteristic point on both sides. And so what will happen is that no matter what small you are, you will form a shock in finite time. Okay. Because you will increase gradient on both sides, and the dissipation is not strong enough to counter that. Okay, so this is the kind of instability you get if you have a bad characteristic point. And the last thing is that you could get an instability of a shock position. Okay, so this corresponds to this sign here. Right, that's quite easy to guess from the linearized Anti-Negonio equation. And yeah, it's not okay. My notion of solution allows for a synchronization of position. So it's not so much the fact that the position is moving, is that as it moves, it erases part of a traveling wave. Like this is a case where at the nonlinear level, what happens is that your position will move, but the profile will not adjust itself to that. Okay, you'll just erase part of the profile on one side and reveal some other part on the other side. So you get quite far from the initial profile. Okay, so these are the only possibilities. So if you exclude all of that, then you have nonlinear stability. So this is the classification. And okay, if under some quite generic classification, generic assumption that the fact that now, okay, to get a full classification, I'm assuming that if there are two anti-dissipative zeros, then they don't share the same velocity. Okay, so let's assume that. If you assume that, then okay, you have only 5 kind of stable waves. each of them with a finite number of jumps. And okay, if you assume something even simpler, like a stronger assumption that F is convex, then you only have three possibilities, like the constant, the Riemann shocks, and the continuous fronts with one characteristic point. Okay, I've already discussed the two first one. I would spend some time now discussing these ones, like the continuous fronts with one characteristic point in the middle. Okay, so let's discuss that a bit. So to describe it, I need to prescribe zeros at infinity, and then the characteristic value in the middle should be also 0, and the sign should be in this order. Okay, like it's dissipative, and in the middle it's anti-dissipative. And I'm assuming that there's nothing else, okay? Because if there's one more characteristic point, it will have a bad sign, and then you get instability. Okay, so this is the only possibility. And then to get a profile, you just have to solve the ODE under this condition. Okay, and then we have proved that it is also non-linear stable, okay, more or less in the same sense. There's a decay rate here that is sharp. And something that is very special is that the shift you have to use does not depend on time. Okay, there's still a shift. It does depend in a nonlinear way from the initial perturbation, but it's not moving. So it's coming from the fact that what you should do is you shift so that you synchronize the value of U bar. I mean, the characteristic value should be the same. No, the characteristic point should be the same for the wave to which you compare on your initial perturbation. Okay, so you just have to synchronize the characteristic value. And then since this is a characteristic value, essentially it's pinned. Okay, it's not moving. So once you have synchronized initially, nothing is happening from on the position. Okay. Okay, this I think I already said. Let me give you just some intuition about what is happening due to characteristic points. And for this, let me use a toy equation. Like, okay, so this is more or less a cartoon of the equation. There's no source term, but here you see it's vanishing somewhere. Okay, the term in front of the dx is vanishing, and I want to see what is the effect on that on the spectrum. Okay, and I use this. Okay, this is a good model locally. Okay, so I'll just look at what happened locally. So in this case, the sign is such, it's a good sign. So the characteristics are outgoing from the characteristic point. Okay, so you should actually, you don't need boundary condition to solve. Okay, you're solving from the characteristic point. Okay? That's more or less what is happening. And I mean, okay, this is easy to solve, so you can solve this explicitly. Okay, there is when you have uniqueness, this is the formula. Okay. But to get uniqueness for this problem, for this to be a solution, there is a condition on lambda. So it should be, the real part of lambda should be sufficiently large. And you see, unfortunately, it's positive here. Okay, so if in LP, this is not good enough to get stability, because to get stability, I want the spectrum to be on the left of the imaginary axis. Here, okay, there will be spectrum also on the right. So what is happening here is that the spectrum depends really on the functional space you should. And in particular, it's depending strongly on the regularity at which you work. Okay? And if you want to move the spectrum, you have to increase regularity. So you may be used to this kind of trick for localization. Okay, like you may know that there is something called convective stability, where instead of looking directly at the spectrum, you use weight so that you move the exponential spectrum to the left. Okay, here for characteristic values, you're doing the same, but with regularity instead of localization. So, and this is actually easy to see also. If you just add k derivatives, you may differentiate the equation k times. And what you've done essentially, you replace lambda with lambda plus k a naught. Okay, and now the condition from before is it's much better. Okay, and if k is large enough, it gets negative, and it's this sign. But then you have to also get the values of the other derivatives, okay, like the first one. And you get them from the equation. So for example, the value here, if you just evaluate this equation x equals 0, you know that lambda v naught, v of 0 should be f of 0. That gives you a value. Okay, and that gives you a value except if lambda equals 0. Because if lambda equals 0, this is normal. At lambda equals 0, you have an element in the spectrum. Okay, but this is happening at other points. Okay, for higher derivatives, you have the same phenomena, but you are creating eigenvalues. So you push the essential spectrum, but you are revealing some eigenvalues in the spectrum. So this characteristic point, it modifies the spectrum in a very strong way. Okay, so it just it makes the spectrum to depend on the regularity at which you work, and it creates some eigenvalues on the road. Okay. So in principle, you're more used to the fact that the large part of the spectrum is determined by what happens at infinity, and maybe you have a few eigenvalues in the middle. Okay, and here it's not like this. Okay, the characteristic points by itself, it creates something directly in the spectrum, and you cannot really remove it. Okay, so on the system case, I would just say that we have now a theorem for Riemann shocks of systems. And here you really have to start with the spectral problem, solve the spectral problem to do the analysis at the linearized level, and then go to non-linear level. Okay, it's much more complicated, okay, but also much more robust, and we expect that with this breakthrough, we'll be able to do a lot of the program for, okay, maybe we need a few years, I don't know, but okay, I think we have now a quite robust roadmap. Okay, I'm almost there. Okay, so I've discussed quite explicitly this case, the case where I'm looking at discontinuous waves of hyperbolic equations, or maybe not discontinuous, but with characteristic points, so all these kind of things. But this is not the only direction on which the stability theory is quite open, okay, and it's widely open. One of the other ones that I've mentioned on the road, and on which I'm working also, but with other people than the one I mentioned before, are the case where you look at periodic traveling waves of dispersive equations. Okay, so this is also completely open. Okay, there's no single result about nonlinear stability of traveling waves in a dispersive equation. Okay, and by this I mean not with periodic boundary condition. Okay, so with periodic boundary condition, there are plenty of results. And I'm thinking about the case that we have seen. Essentially, if you think about the channel is more like, when you see it, it looks infinite. Okay, and then so you're on R, and then when you perturb somewhere. You don't perturb in a periodic way. Okay, it's just so the stability result you are looking for is exactly of the kind I've mentioned before. You add a localized perturbation to something that is periodic. And for dispersive equation, we are more or less okay. Well, we are working, but we are more or less at the stage where we know how to go from spectral to linear, and we still need to work to get some example about nonlinear case. And since the decay is due to dispersion, the higher the dimension, the easier it will go, except that you need spectral stability. Okay, you probably know that in many cases, when you go to higher dimension, you can create transverse instability. Okay, so there's a kind of trade-off where you need to look at a case where you don't have transverse instability, but you can play with the dimension to increase the dispersion and close the nonlinear argument. Okay, so I will not say much more about this. Thank you.
Thank you very much. Any questions for our speaker?
I probably put the microphone.
Well, so they can hear online.
Okay. Oh, right. Yeah.
There's a group online.
Right. So did I understand correctly that even for something like KDV, you don't have nonlinear stability of periodic traveling waves?
Yes. I
So
mean,
even
okay.
like
No, yeah. Okay. Yes or no. Yeah. Okay. I should have said that there are some results where you study large time by integrability techniques, but they are not formulated in terms of
maybe
stability.
I should say generalized KDV then.
Yeah. Okay. For generalized KDV, yes.
Yeah, okay. All right. Interesting. Some good challenges there.
Other questions? Folks online? So I guess if the periodic traveling waves in dispersive equations are hard, the DSW is going to be even harder.
Okay, my true answer is yes, but I should say that what is different is that what you try to justify is not something globally in time. Okay, so it's closer to the mixing example of ODs I've given, like you scale with one over epsilon. So it's yeah. So I think it's probably harder, but it's also a bit different because it's not infinite time. It's sufficiently long time. Then, okay, and that actually matters when you, and for the, okay, maybe I can say a few words, but to lower the dimension and to get to really interesting dimension, I'm expecting that we'll have to use things like normal forms and space-time resonances and so on. And these kind of techniques, they are much better at proving things where we are on some finite but long interval than global in time. And so it's, okay, so yeah, I think it's harder, but I also think that there are some points that are easier.
Okay, well, if there are no other questions,
I have
I
a
guess
question.
let's thank Miguel again, and we'll wrap up.
Hello?
And we have a seminar tomorrow at 11 in this room, subject to noise on the elevator out there. They're doing some work. So assuming it's not too loud, we'll be in here tomorrow for Pavel Leshnikov's talk. Okay. Have a good afternoon.
Yeah.
Hey, Nathan, are you there?
Then you have some parameter.
Yeah.
Hello?